Hello everyone, and welcome to Shimadzu's Theory and Key Principles series. This is one of a series of lectures focusing on gas chromatography. The key topic for today will be the splitless injection. For this session, I'll be your presenter. My name is Andrew Clissold, and I'm the GC Business Manager for Shimadzu here in the UK. As before, please submit any questions you have on the left-hand side. We'll be sending out a short feedback survey after this session, which also contains a quiz so you can test your knowledge from the webinar. The survey also gives you an option to request a certificate, if you'd like one for your records. This is the third session in our Theory and Key Principles series on GC. If you missed any of the previous sessions, I recommend you watch them and then sign up to the next available slot for this session. You can watch all our previous sessions on demand by visiting our website. Please continue to join us over the coming weeks, where we'll be further developing our knowledge and understanding of GC. We'll discuss the various advanced liquid and non-liquid injection techniques, detectors, data processing, as well as maintenance and troubleshooting. In this presentation, I'll be focusing on the most common GC inlet, the splitless. This is a really important session, arguably the most important in the series, especially for those of you using GC. If you get it wrong here, it all goes wrong. The vast majority of technical issues a GC system has are incorrect use of this device. Your choice of method parameters will have a huge impact on the final result. So an understanding of how it operates is very important indeed. We're going to start off with a basic overview of the component parts of an inlet and the fundamental concepts. We'll do this using a more simple packed injector initially. Once this is understood, we'll move on to why almost all GC systems use a splitless inlet. As its name suggests, it can operate in two modes, so we'll cover both of them, how they work, when to use one or the other, and the key method parameters for each. Finally, we'll take a look at how to best utilise the carrier gas saver mode, a feature most modern systems include in their software. So let's go back for a moment to session 1 and recap very quickly what the GC inlet does. The GC inlet, or injector as it's sometimes referred to, acts as an entry system into the column. It's where the liquid sample is introduced into the system via a syringe. As we discussed in the first session, a pressurised gas is needed in order for the GC to operate correctly, and this gas pressure is regulated by an electronic device, usually installed in the rear of the GC, called a flow controller. Here's a schematic of one on the left. This complex and highly intricate device manages the pressures and flows of gases into and out of the inlet. This pressure management is used to control the speed and flow of carrier gas into the GC and down the column. The next time you ask your GC to run a particular method, what you're actually doing is sending a series of instructions to this device, telling it what pressure and flow you would like it to provide. On the right here is approximately what a GC inlet looks like. It doesn't matter what brand of GC you have, the basic design is the same. The inlet is fitted to the top of the GC, with the upper section protruding out the top, so it's easily accessible for an analyst or an autosampler. A series of gas pipes connected to the flow controller from the previous slide. This supplies the inlet with carrier gas to feed into the column. At the top of the inlet is a septum nut. This is a cap with a small hole in the centre, allowing a syringe to pass through when a sample is injected. Below this sits the septum. This rubber stopper keeps the inlet sealed to maintain pressure while still allowing a sample to be injected through it. Inside the inlet sits a hollow glass tube called a liner or insert. The liner is one of the most important parts of the inlet, as it's where the sample is rapidly vaporised from a liquid to a gas. It's also where it then mixes with the carrier gas. Often the glass tube will have a small plug of glass wool inside, so that when the liquid is injected, it coats the wool to create a large surface area. This helps to speed up the vaporization and mixing to give the best possible peak shape. The glass tube and any wool usually undergo a chemical process to deactivate the surface so that the sample doesn't react with the glass. We'll cover how to choose the correct liner during our maintenance and method development sessions later in the series. Sitting around the outside of the liner is a rubber O-ring. Its job is to hold the liner centrally within the inlet and to act as a barrier to prevent carrier gas going around the outside of the liner. For correct operation, the carrier gas needs to flow downward through the inside of the liner to sweep the sample onto the head of the column. The column connects to the bottom of the inlet from inside the GC oven. It's held in place with a column nut to ensure none of the carrier gas can escape. In this graphic, we've got a packed column connected, which is usually a similar diameter to the liner itself. We'll cover sample introduction onto both packed and capillary columns in the coming slides. In order to mix our sample effectively with the carrier gas, the liquid sample must vaporise into a gas very quickly and as uniformly as possible inside the liner. To achieve this, the inlet needs to be heated. If this doesn't happen, it can result in very poor reproducibility, with peak retention times in areas changing from injection to injection. It can also result in very wide peak shapes, which, as we know from the last session, is less than ideal. To ensure all components within the mixture vaporise quickly and fully, the inlet is usually heated to between 200 and 300 degrees, depending on how volatile the mixture is. Again, this is something that will be discussed in more detail during the method development session. Now, for those of you who've created GC methods, or looked at the method your system uses, you may have noticed a parameter called Septum purge. When we heat the inlet, which also causes the rubber septum to get hot, it starts to release chemicals which most GC detectors will pick up. This means even if you don't inject anything, we might see peaks on our chromatogram. These peaks are often referred to as ghost peaks and can be problematic. To try to minimise ghost peaks caused by the septum, most inlets have a second exit point for the carrier gas to escape from, a septum purge line. This pipe is connected to the upper portion of the inlet body and allows some gas coming into the inlet to flow over the underneath of the septum and straight back out again. Critically, this flow does not go down the column. The pipe connects back to the flow controller and is regulated like all other parts of the method. The septum purge flow rate is small, typically only a few mils per minute, and is sufficient to effectively sweep away any chemicals from the septum. These components make up the most simple inlet that can be used for gas chromatography, the packed inlet. As the name suggests, these inlets are designed for use with packed columns, but can also be used for very wide bore capillary columns, where the internal diameter is around 0.5 mm or more. With a typical packed column, the carrier flow rate, to give optimal separation, is around 30 mils per minute. If we combine this with our 3 mils a minute of purge flow, we end up with a total flow from the flow controller of 33 mils per minute. Let's now look at what happens when we inject our liquid sample. The standard injection volume for a GC is around 1 microliter. It's a very, very small amount. So the injection is performed using a microsyringe, usually with a total volume of 10 microliters. There's a very good reason why we inject such a small amount. 1 microliter of liquid, in this case we'll use hexane as a solvent, expands significantly when it vaporizes. Under standard conditions, this would produce nearly 250 microliters of gas vapour. It's absolutely critical that the volume of gas created is less than the internal volume of the liner. I cannot stress how important this is. A typical liner has a volume of around 500 microliters. Actually, that's not true. It's usually a bit more, around 700 or 800 microliters. But to simplify the maths and the calculations, we're going to work with 500 for now. So as I said, 1 microliter of hexane expands to 250 of gas under common analytical conditions. This is fine, 250 is less than 500, so we're well below the maximum volume of the liner. What happens though, if instead of hexane we used a more polar solvent like water or methanol? Well, in this case, 1 microliter of water expands to nearly 2,000 microliters of vapour. This is hugely greater than the volume of the liner. If, or when this happens, the sample cloud expands into whatever space it can find. This means that, as well as going onto the column, it can travel down your septum purge line, and even back up the pipe supplying your carrier gas flow from the controller. This is what's known as backflash, the flash vaporization of a solvent down pipes and tubes connected to the inlet body. Whilst the inlet is heated, these gas lines are not, so your sample can begin to condense inside these pipes. This lost sample can cause a host of problems, from ghost peaks, blocked pipes, to damage of critical electrical components. This is one of the most common mistakes made when using GC. Sometimes the analyst is trying to boost the sensitivity by increasing the injection volume, and doesn't consider the expansion coefficient of the solvent being used. We'll cover more on this during the troubleshooting and method development sessions. For now, to avoid this cardinal sin, it will be worth taking time to calculate what the safe injection volume of your method is. ResTech and Trajan are 2 column suppliers that also have online calculators. These can be used to tell you what your safe liner expansion volume is. At the end of this session, why not go away and plug your method parameters into one of these calculators, check the expansion volume, and see whether you're injecting too much. So we've discussed how the liner volume is key to the amount that we can inject without causing backflash. But it also plays a role in peak shape. As we've discussed, the inlet is the entry point to the GC column. The transfer of sample as a gas from our liner onto the column is very important. Our pack column has a flow rate of around 30 mL per minute, meaning we can flush the contents of the liner in just 1 second. This means our sample bandwidth is 1 second at the head of the column. As we know from our last session on columns, as a compound spends time on the column, the peaks broaden. So if it starts at 1 second, it's safe to assume that by the time it reaches the detector, it will be wider than 1 second. Now for packed columns this is okay, because we're expecting wide peaks anyway, perhaps around 10 seconds, depending on the column conditions. Talking about packed columns, however, is only so useful. As we now know, capillary columns account for 95% of modern GC columns. These are much smaller than their packed cousins, and offer some unique challenges for sample introduction. This is why understanding how splitless injectors work is so important, as they are designed specifically to work with capillary columns. You might think that switching to a capillary column would make no difference. Why can't we keep using the same packed inlet we've used so far? Well, for starters, the inner diameter of a capillary column is much smaller than of a packed column. If we were to apply the same 30 mL a minute of flow that we used for the packed column, we'd need an incredibly high pressure. This would create a wealth of problems by itself. More importantly, the linear velocity of our carrier gas, that's the speed it travels down the column, would have to be incredibly high. This would result in very poor peak shape and virtually no separation. And remember, the whole point of these capillary columns is to exploit their greater separating power. So we must reduce the column flow rate. Around 1 mL per minute is normal for a standard capillary column. However, this creates a new problem. At 1 mL per minute, the transfer of sample from the liner to the column is much slower. This time it takes 30 seconds rather than 1. This produces a very wide peak that is no use to us. The next issue we're confronted with when moving from packed to capillary is sample loading. This is the amount of substance we have on our column. In pack columns, there is a large amount of packing material covered in a large quantity of stationary phase. With capillary columns, the stationary phase is coated in an extremely thin layer around the inside wall. This means the amount of stationary phase available is much smaller. Imagine if your stationary phase were a towel and your sample were a jug of water. If we slowly pour the water onto the towel, it absorbs all the water and none of it drips on the floor below. This is your pack column example. Now, if we compare that to a capillary column, we've got the same amount of water in the jug, but this time our towel has been replaced with a much smaller one. As the water is poured onto the towel, it quickly saturates and the water pours through. The very same thing happens if we try loading our column with too much sample. The stationary phase saturates and our sample just keeps going. This again leads to very poor peak shape. The lesson here is that capillary columns simply cannot handle the same amount of sample as their pack column predecessors. So then, it's starting to sound like capillary columns are more trouble than they're worth. Fortunately, there's a solution for both these issues. We just need to add another pipe to our inlet, a split line. The split line does as it says, it splits. It acts as an escape route for excess flow that we can no longer send down the column. This means we can maintain a flow rate of 1 ml per minute while still flushing our liner with 30 ml a minute. The high flow means the transfer of sample is quick, giving nice sharp peaks. The remaining 29 ml per minute coming down the liner is diverted along the split line instead. By doing this, only a fraction of our sample goes onto the column, giving us an automated sample dilution. As with the septum purge discussed earlier, the split flow rate is regulated by the flow controller. The way the flow controller regulates the split flow and the septum purge is a bit like controlling the flow of air out of a balloon. If you make the opening bigger, the air rushes out faster. In the same way, the flow controller alters the size of the hole to adjust the rate of flow through the split line. So our flow controller is really the brains of the operation. It ensures that the correct flow rate is supplied at the correct pressure and that the flow rates leaving the inlet via the purge and split flow are the correct values. Interestingly, one thing it can't measure is the actual column flow. This value has to be calculated based on the inlet pressure and the dimensions of your column. This is why when installing a column, it's extremely important that the dimensions entered in the software are correct. If not, what the software tells you is happening and what's actually happening will be different. The idea of a split line can seem quite odd at first, so if you're feeling a little confused by all the wet tea towel and balloon analogies, don't worry. Let's look at an example of how to use a split line with our sample. When we do this, we're using a splitless inlet in split mode. That is, we're splitting our sample and sending a large portion down our split line to waste. The key parameter in a split injection is the split ratio. This is expressed as a ratio between the total flow down the liner and the flow down the column. The purge flow is not really involved in calculating the split ratio, so for now it can be ignored. In this example, there's 30 ml per minute travelling down the liner, and 1 ml a minute of that down the column. So that's a 30:1 split ratio. This means, for every 30 portions of your sample, only 1 goes down the column. Here's a question. What would happen if we increase the split ratio? Let's increase it from 30:1 to 100:1. We can still only put 1 ml a minute down the column, its dimensions haven't changed, so this still represents the optimal linear velocity. Now our total flow rate is 103 ml per minute. That's 3 for the purge, 100 down the liner, and 99 escaping out the split flow. The important information is how does this affect peak shape? An increased split ratio allows the sample to transfer to the column more quickly, so the peaks get more narrow. However, as the volume of sample making it to the column is now smaller, the peaks will also get smaller. Setting a smaller split ratio would have the opposite effect. The advantages of using a split injection are clear. It allows us to inject samples into capillary columns, while keeping the peak shape nice and sharp. It also allows us to adjust the amount of sample moving onto the column. Now, all of this is great, but the split line does come with some drawbacks. Firstly, we've introduced another outlet to our system. It's hard to justify a consumption rate of over 100 mL a minute when only 1% of this is actually making it down the column. This is especially true if the carrier gas is helium, given its high price and dwindling supply. Fortunately, there is a fairly simple fix, and we'll discuss carrier gas saver in a few slides' time. The second, and more worrying problem: what if my sample concentration is already so low that I cannot afford for the inlet to dilute it? Many modern applications require very high sensitivity, and a sample inlet that dilutes your sample is a bad idea. So what do we do when dealing with samples that are already pushing the limits of detection? There is absolutely no way we can spare any of the sample. As it happens, adding a split line is not the only way to maintain peak shape. We can actually work without one, in a different work mode called, yes, you guessed it, Splitless. Now, fear not, everything I said in the previous slides about needing a split line is true, most of the time. But there are occasions where we can get away without needing one. Split mode is your go-to technique for 99% of applications. It's easy, it works well, and there are far less traps and pitfalls, so if you can, use it. However, for situations where the amount of sample you have simply doesn't allow it, let's talk splitless. We don't remove the split line, this would be time consuming and fiddly, but the flow controller simply closes the hole fully so the split flow is zero. We already know we can't increase the column flow, so we need to accept that it's going to take around 45 to 60 seconds to flush the sample from the liner onto the column. Fortunately, we can exploit a trick known as solvent focusing to fix the problem of running without the split line. So how does this solvent focusing effect work? Well, we carry out our injection as normal, so the sample vaporizes in the inlet and slowly transfers itself onto the column in a long, drawn-out band over about 1 minute. Crucially, all of the sample we injected is now being transferred onto the column. We're not sending any along the split line at all. In this example, our solvent is blue and our analytes are in red. As you can see, they transfer onto the column in a vapor gas cloud. Very importantly, the column oven temperature is kept cool. Specifically, it's usually kept around 20 degrees below the boiling point of the solvent. By doing this, as the sample continues along the column, it begins to condense back into a liquid. The liquid solvent redissolves the analytes, so that they no longer dissolve in the carrier gas. This liquid coats the inside wall along the first metre or so of the column, trapping the analytes within. Once transfer to the column is complete, the oven can begin to heat up. This causes the solvent to move along the column, and drags with it the dissolved analytes. However, as the oven temperature continues to rise, there comes a point where the solvent evaporates off, leaving behind a nicely bunched up set of analytes. For this to work, the boiling point of the analytes must be at least 20 degrees higher than the boiling point of the solvent. If this strict rule is not followed, the analytes will just move with the solvent as it evaporates and never refocus. So, by reducing the oven temperature below the solvent boiling point, waiting for all the sample to transfer onto the column, and then heating the oven up, we're able to use the solvent to refocus the analytes into a very small band, which gives them nice, sharp peaks. Remember that this is reliant on a solvent that is much more volatile than the compounds. In most circumstances, it is also necessary to keep the initial oven temperature 20 degrees or so cooler than the solvent boiling point. As you can see, Splitless requires some very specific situations in order to work well. This is why in most applications a more simple split mode is used instead. We've now covered everything you need to know to set up a technically correct split or splitless method. The splitless inlet solves almost all the problems that getting sample onto a capillary column can throw at us. You'll remember a few slides back that I indicated there was another drawback to split injections: increased gas consumption. For that, we also have an easy solution. In this scenario, we're operating the inlet in split mode. The split line is open and consuming 99 mL per minute of gas. If the carrier gas was something cheap, like hydrogen or nitrogen, then that's not a huge issue. But it still means we're consuming gas cylinders at a faster rate. This is expensive and wasteful. So, wherever possible, we want to conserve gas. Fortunately, modern hardware and software usually comes with a feature called gas saver mode, which does just that. In a split method, we use a high split flow rate in order to speed up the transfer of sample onto the column, and to dilute the sample. Once a sample is on the column, however, what does a split actually achieve? The answer? Not much. In a typical split injection, the sample transfer to the column is quite fast. This means that shortly after injection, the split ratio is no longer required. We know that changing the split ratio does not affect the column flow, only the split flow. A modern split inlet can handle split ratios down as low as 5:1. Typically in your GC software, there will be an option to activate gas saver mode. This reduces the split ratio to a lower value of your choosing, typically 1 minute after injection. The same function will return the split ratio to a higher value, ready for injection of the second sample. This is more useful than it sounds. Smaller split ratios require less gas to operate, so by running in a small split whenever possible, the consumption of gas is minimised. Okay, that's the basics of the splitless inlet. It can be a difficult concept to understand at first, but it's critical to know how this device operates. Let's recap over some of the key points. The splitless inlet is optimised for use with capillary columns. It comprises of a nut and septum, liner and O-ring, a heated body, and has a septum, purge and split line. The most common operating method is split mode. This speeds up the transfer of sample onto the column and dilutes it down prior to use. The split ratio defines the sample dilution. The higher the ratio, the less sample is transferred to the column. Higher split ratios therefore give thinner, sharper peaks. Splitless mode is used only when sample concentration is too low to allow a split. The split line is closed to facilitate full sample transfer onto the column. It relies on solvent focusing to give a thin band of sample. And finally, carrier gas saver helps reduce gas consumption by reducing the split ratio when not required. That's everything for this session. As always, if you have any questions, please do submit them on the left-hand side. Following this webinar, we will be sending out an email to all participants. This should be within the next 48 hours. Included in the email will be the answers to all your questions and a copy of the slides for your notes. You'll also find links to a short feedback survey and a quiz if you'd like to test your knowledge. If you'd like a certificate for the course, please complete the quiz and one will be sent to you automatically in the next month. There'll also be links to register for the next session. On that subject, the next session will cover advanced liquid injection techniques. In this we'll be covering when splitless is unsuitable. We'll look at programmable temperature vaporization, on column injection, large volume injection, and multimode inlets. Please do join us. In addition, if you'd like to learn more from Shimadzu, please do join our mailing list. Alternatively, all information is available from our UK website. If you'd like to get in touch with Shimadzu, please see our contact details for the UK office. For those of you joining from outside the UK, you can find contact details for your local Shimadzu office by visiting Shimadzu's global website. Just go to www.shimadzu.com/an and click on the contact search in the top right of the screen. That's all from me for this week. Thank you very much for your attention and enjoy the rest of your day.
Excellence in science. Shimadzu.